Okay, in this video we're going to consider once again combinations with repeats, and we're going to consider the same identical problem as we just did in the previous video, only now we're going to solve it using generating functions, an entirely different approach, and as hopefully you will see, it is an approach that is very powerful. And the problem that we considered in the last video was, suppose that we have 6 crates that are filled with candy, and each crate has a different flavor of candy. So this might be cinnamon, this might be cherry, this might be vanilla, this might be apple, and so forth. And we said, well, if we have, say, 6 crates that are just filled with hundreds of pieces of candy, how many different ways can we select 10 different pieces of candy from among these 6 different crates? And in the past video, we found out that the solution to that is this expression, where N is the number of crates that we're choosing from, or the number of flavors that we have to choose from. In general, N denotes the number of objects or the number of things that we have to choose from, and K is the number of selections that we're going to make. So in the past problem, we had 6 crates filled with candy, so we had 6 crates to choose from, or 6 flavors to choose from, and we could make 10 selections, so K corresponded to the number 10. Now here we're going to consider the same problem, only now we're going to consider it from the viewpoint of generating functions. And let's just say that here we not only have 6 crates full of candy, but let's say it goes on now so that we have a total of N crates filled with candy, and we're going to select K, number of pieces of candy. How many ways can we do that? Now, if you've looked at the previous videos, you know that the first thing that we try to do is, for each one of these crates, is describe the situation by way of a generating function. So the first crate we can imagine is filled with hundreds of pieces of candy, and we could say, all right, let's just look at the problem now from the viewpoint of this one crate. From that one crate, how many pieces? We might choose 0 pieces of candy, or we might choose 1 piece of candy, or we might choose 2 pieces of candy, or we might choose 3 pieces of candy, or we might choose 4 pieces of candy, and we can keep going like that. We are imagining now that we have an unlimited number of replacements there. So that situation then, where from that first crate, I'm saying, well, yeah, I could represent it like this then. I might not choose any, or I might choose 1, or I might choose 2, or I might choose 3, I might choose 4, whatever. And this, as we noted in previous, in the past videos, this infinite series is equal to when x less than the absolute value of 1. And when we first discussed generating functions, we said, yes, these variable x's, we can attach whatever value we want to them. So without loss of generality, we can certainly assume that these x's are indeed less than 1. So the generating function for the first crate is this. Well, it's the same situation for this crate, for this crate, for this crate, for this one, all the way on out to the nth crate. And as we noted in the previous videos, is that then if we want to consider all the crates together, and we want to say, well, of these n crates, then we want to make k number of selections. And the way that happens is that, first of all these individual generating functions get multiplied together. So we would have 1 over 1 minus x times 1 over 1 minus x times 1 over 1 minus x, and we would have n terms like this. Or that would equal 1 over 1 minus x to the n. Now, what we're interested in then, if we're going to select, and remember what n is the total number of crates, or n is the total number of objects that we have to select from. If we're going to select, in the past video we said, well, we have 6 crates and we're going to take 10 pieces of candy. Let's just say in general we're going to select k pieces. Of candy. So here we have n crates. When we consider the situation for each crate, the generating function, that is represented by this, which is represented by this function. So we multiply all of them together, we're going to get this expression. Now, and we'll say, okay, we're going to select k pieces of candy. How many ways can we do that? Then the answer to that is, it is equal to this is just this. Now we need, in this expression, we need to find the coefficient of x to the k, just like we did in the previous videos with the simpler kinds of problems. Okay, and how do we do that? Well, if you've been following the series, you know that we've had several videos denoted that we covered the binomial theorem when we had positive exponents as well as negative exponents. And if you missed those videos, if you go to the website at digital-university.org, all the videos concerning combinations and permutations and probability problems, they're all listed there. They're all presented for you there in their proper sequence. But what we did in those previous videos, you may recall, for example, that a plus x to the n, when we used the binomial expansion theorem, we got this expression, which we could write very compact like this. Or, instead of a plus x to the n, if we had just 1 plus x to the n, now this is just equal to 1, so we could write it like this, or 1 plus x to the n, that equals this. And again, we've worked with this in previous videos. What we want to point out is that when this is a positive exponent, this then will be a finite sequence. Now, when we had a negative exponent, this was the expression we got. And let's just look at it for a minute. Here, this, of course, we have the binomial coefficient of n minus 1 over n minus 1. That's just 1. We write it like this, though, so that we can remember what the pattern here is. So it's this binomial coefficient times a to the minus n. Then as we go through the series, this part of the binomial coefficient stays constant, and then this part here, we continuously add 1 to it. So for the next term, it's n over n minus 1. The exponent here decreases by 1, so you have minus n minus 1, which you write as minus to the n plus 1, x to the first power. Now the exponent for the term x, that continues to increase by 1. So as we go through the series, we add 1 to this, we add 1 to this exponent, and we subtract 1 from this exponent. So the next term is n plus 1 over n minus 1, a to the minus n plus 2 times x squared. The next term in the series is n plus 2 over n minus 1, a to the minus n plus 3 times x cubed, and this keeps going all the way out to infinity. And again, this situation we can write in a compact form with a negative binomial coefficient, a to the minus n plus k times x to the k, and again, with a negative exponent, this is an infinite series. Now, if we have 1 minus, incidentally, here, all these terms are positive. If we had a plus x, then we'd be having alternating plus and minus terms. This would be plus, this would be minus, this would be plus, that'd be minus, and so forth. Now, when we have just a is equal to 1, and this is what we have for our generating function, this is equal then, this is just 1 to the k, then here we have minus 1 to the k, and the reason, and also we should have that up here too, as minus 1 to the k, and the reason for that is these are alternating plus and minus as we go out the series, alternating plus and minus. So you multiply by 1 to the minus 1 to the k, then you get all positive terms, which is what they should be. But here now, this binomial coefficient minus n to the k, as we noticed in the previous videos, we can denote it like this, that's the same thing, but what we showed in the previous videos is that this, which is this, we're writing it like this now, is equal to minus 1 to the k times c to the n plus k minus 1 over k. Well, back here then, in our expansion, we had minus 1 to the k times that. So if we have minus 1 to the k times this, then on this side we have minus 1 to the 2k. Well, that's raised to an even number exponents. That's always positive now. So we have this expression. So what that means then is that this 1 minus x to the minus n, which is our generating function of this problem, can be written like this, as this infinite series. But lo and behold, look what you have. In general, for x to the k, its coefficient is c to the n plus k minus 1 over k. Well, that's the same thing as this expression right here. And as we showed in the previous video, except that we're missing an explanation sign, this is n minus 1 k factorial, not times k. N minus 1 factorial times k factorial. Well, as we showed in the previous video, this is the expression when you are having a combination problem with repeats. When there are n objects to choose from, and you can choose them with repetition, and we're selecting k of them, we said that the solution to that is n plus k minus 1 factorial divided by k factorial times n minus 1 factorial. And if we just showed you this indeed is the coefficient of x to the k in this expression here. So this same problem, when we're considering, say, crates of candy, and you can select 10 pieces of candy with repetition, you can take 2 from here and 3 from here and so forth. There's no restrictions. The number of ways that you can do that is this formula, and once again, that formula that we once again derived in the previous video, this expression turns out to be the coefficient of x to the k in this function right here when we expand that out. So we get the same answer when we approach this problem from the viewpoint of generating functions. Now, the advantage of this approach is, suppose, for example, we had some restrictions. From the first crate, let's say, didn't matter, we could take as many as we wanted, but maybe from this crate here, we say, all right, here you have, say, 6 crates of candy. So n equals 6. And you can select, say, 20 of them. So k equals 20. But when you're doing it, you have to include at least 3 pieces from this one. And from this one, you can only select an even number. Now, how would we set that problem up? Well, for this crate, where there's no restrictions, this one, and this one, they would all have the same generating function. So we'd have 1, 2, 3, 4. So we would have this, which is to the 4th. But now we have to consider the generating function for this one and for this one. Well, for here then, this has to start with x cubed. We do not select, we say that this has to have at least 3 for each selection. So we can't say, well, we could take 1, we could take 0, or we could take 1, or we could take 2. No, it has to be at least 3 from this crate. So we have this so far from this crate, this one, this one, this one. Now the generating function for this one is x cubed plus x to the 4th plus x to the 5th plus x to the 6th, and so forth. Notice we do not start with 1, because 1 means that we have the option of not selecting anything from that barrel. No, now the restriction is we have to take at least 3 from that barrel. And from this one here, we also have to include in our distribution every time an even number from that barrel. So that would be x squared plus x to the 4th plus x to the 6th plus x to the 8th, and so forth. So this would be the generating function for this barrel with that restriction. This would be the generating function for this barrel with the proviso that we have to take even number of pieces of candy. Now we have to consider, we have to multiply these together and then find the coefficient of x to the 20. And that's going to be more difficult than what we did before, but again, in the future videos, we'll learn how to handle this situation. What we're trying to do right now is just kind of demonstrate how powerful the generating functions are in solving these combination problems with repeats. And again, in the future videos, we'll have some specific examples where we'll cover it in more detail. Okay, anyway, that's it for this video. Come back Join us for the next videos, and we'll try and solve some more problems.